glad that I finally managed to come to this data. What I'm talking about today is really pushing the frontier a bit. It's getting a bit exotic. It's getting so exotic that one of my students who wanted an exotic topic wrote on paper and I decided, no, now he wants to work on fermions and Habermas. The basic question started 4 years ago when Mike Friedman wanted to understand what is the Heisenberg model. And in his math language, he explained to us what he believes is the Heisenberg model, and we just stared at him and asked him, can you please explain all the words in your sentence? And that first was the Troy project, but we soon found many nice connections between anyons, quantum Hall, spin models, and the Sedgwick problems. And I want to give you the finding over to work with it, with a few people of whom one is here, Eddie. And basically, we are dealing with models built not from the bosons or the fermions, but from anyons. And the anyons we want are the 1 billion anyons. When you break to a billion ones, you simply get a phase. While for 1 billion anyons, the ground state of the many anyon problem is degenerate, and the braiding acts like a matrix, and those matrices don't commute. Why is that pretty interesting technologically in the future? It's because one can show that for most types of the 1 billion anyons, the action of the braid group is density of SU2, so you can do any quantum computation just by braiding particles. They are far away, well-defined, don't interact, and there is no source of error here. So if we find them, realize them, then we can build the quantum computer. But first of all, we have to find them, and the question is where do they exist? The simplest ones are the Majorana fermions or the Ising anyons. They might appear here. With the superconductors in some quantum Hall states, or in the honeycomb model by Kit Dive. Then, but with them it's hard to make a quantum computer. The better is, if you put the anyons, they might be in the 12th quantum Hall state, and in some very artificial spin models like the Leibniz model, and all those particles are representation of the quantum group SU2 level 2, level 3, or level k. And when k goes to infinity, then we recover a standard spins. Now, since some of them might not know what SU2 level k is, let's say a quantum deformation of the SU2, and essentially it's that there is a cutoff in the highest possible spin in the representation. Level k means it is cut off at a spin of k half. So when we fuse spins, like we take a spin J1 add it to a spin J2, then for ordinary spins it goes from it goes up to the sum of the two, but here in this case it is truncated by the cutoff. So let's say we have a k that is only 2, then we have only spin 0, half, and 1. That means we can never add spins to have more than a spin 1. What are the fusion rules then for two spin halves, they can form a singlet or a triplet, a spin 0 or a spin 1, as soon as the spin 1 exists, so when k is larger than 2. When we add two spin 1s, then we usually get a spin 0, a spin 1, and a spin 2, but only if k is larger than the equal of 4, so that the spin 2 exists. If not, it's just 0 plus 1. So, and then once we have them, the 6J symbols are modified and so on, but in principle we can work with them as if they were spins. Where might they appear? As you 2 level 2, so with the cutoff at the spin 1 can appear in the vortex cores of P plus P negative the superconductors. There's this here, the sigma particle, there's the spin 1/2, and there's there's a fermionic particle, the spin 1, and there's a trivial particle, the spin 0. The quantum Hall case.
Can you go back a bit? I'm not sure. What do you mean by sigma vortex?
In the core, so the core of, so if you take two the vortices in this people plus I the superconductor, then there's the zero mode in the vortex. So the two the vortices combined can be either in that state 1 or the state psi. So when you look at the set of your vortices, then the ground state of the vortices is 2 to the n½ fold the generate, because there's this anion living in the vortex core.
Which is to say Majorana. Which is to say a Majorana in this case.
Majorana in this case, yes.
How do you combine two vortices? They just overlap, or?
We create them in pairs and just they are in this state. In singlet or triplet.
Zero field, right?
Yeah. Yeah.
And what's the difference if you put in quotes, half flux, you put in quotes there? You see, it's not the real flux. You say sigma vortices carry quote unquote half flux. Why do you put it in quotes?
I took the slide from
The second line from
yes,
the left.
Why is it more than close?
Why it's in quotes?
Actually, I don't know, because I took the slide from Simon.
One way to get the half flux is to have a spin pull system and let the spin twists kind of around the space, and then also have a not a full flux but just half flux. And that way in spin up you have a full flux form. In spin down you have no full flux form. So but you need this then in the gap parameter just a half flux. I think that's the reason.
Yes. Okay, or for the quantum Hall states, nothing is clear yet, but there have been proposals that in the 5½ state there are some theories by Moore and Reed that give you your Majorana the excitations, and for the 5th case there might even be the Fibonacci particles representations of SU2 to level 3. Nothing of this is really clear yet experimentally. The search is going on. There's some evidence that the Majoranas might be there, but so far it's still very uncertain. But the search is going on. What we still want to know is what happens once we have a set of those anions. Let's take them, let's cook with them, let's make a soup. And what are the states that appear? What one usually assumes when one talks about quantum computing is we take those anions, they are pinned somewhere, localized, they're stuck there, they're forming a Wigner crystals or the pin somewhere. And for quantum computing, we assume that the distance between them is very large. When the distance is large, they don't interact, and the ground state has macroscopic degeneracy. And when we now take one and braid it around, then we can have the quantum computer. But what we're interested in now is we don't want to separate them so far, but we want to bring them closer. And so close that they start to interact. Because in any device, they might come close at some point, so we want to know what happens then. The fermions, when they don't interact, are boring or bosons. So here let's do anyons and let's bring them closer and let's see what can happen.
I have a question,
Yes.
something which I never understood in this regard. So anyons are defined for non-abelian anyons
Yeah.
are defined as particles such that you fix them and then there is exactly the general set of wave functions and they mix as you braid them. But now
Without
once-
interactions.
But once you bring them close, somehow the degeneracy splits. At that point, they're no longer anyons; they're just regular particles. Why are they still anyons?
They are those anyons, which is these localized particles, and now we bring them closer, and we see what happens. Do they vanish or not?
I mean, I guess the number of states in the Hilbert space is still.
It's okay.
Yeah.
So
Yeah, they
yes,
split. And
Okay.
somehow, I don't know,
What
how they define
we have is the following: we have the space of the anyons with a certain degeneracy, and then there's a gap above that.
Yeah.
The quantum Hall gap or something.
The opposite infinity and the anyons. but-
And now we just look at this ground state sector, we start splitting it a little bit. And we want to check what happens with those anyons down there. Do they vanish? Do they just become fermions? What happens? But there's still the gap above. Yeah.
In the long wavelength limit, can I think about it just as if I put a set of anyons and they start interacting,
Yeah.
then it's just like forming two boundaries because basically so it's basically two interacting edge theories, isn't it the same? In the
Yeah,
long wavelength
we're coming to that, yes. Yes, that's one thing that might happen, yeah.
So I don't know at what stage you're going to talk about the method, but what exactly are you going to do?
The method is we're going to do exact coordination, DMRG, exact solutions per beta ansatz, mappings to CFTs.
So how do you manipulate it? By driving the potential in the layers? Or?
First we have to define the model, what happens when they come closer. And then we discuss what we do next, okay? So what might happen? One thing that might happen is when they bring too close, they just vanish, annihilate each other, form a fermion or something boring, and they're gone. It's just the vacuum that's left. Another thing, we might get some gapless state, some gapless liquid state or something. We might get a crystal maybe, or as Ehud mentioned, we might get some new liquid get nucleated and then an edge around it. There are many things that might happen. So what's going on? And let us now first define a model of what happens when two particles interact. And that model will take phenomenologic first by a comparison to standard spins of fermions. When you take two localized spins, they spin 1/2, we bring them close, they start to exchange, and the total singlet state and the total triplet state of the two spins might have a slightly different energy due to the tunneling processes. The same might happen here. If we take two spin 1/2 anyons and bring them close, their energy might differ depending on whether they are in a total singlet or triplet state. So we get a Heisenberg model as the lowest order term that it is.
What is the sign of G? Do you assume a specific sign?
The next slide. It will come. We don't. So it turns out that the sign depends on the realization at the end.
So the reason I'm asking is that there was some work which suggested that the sinus actually oscillates as
Yeah.
a function of distance, and the length scale of the oscillation is the smallest length scale in the problem. So the question is whether you can actually localize your anion to such a degree at all, so that it's meaningful to assign a particular sign at all.
We can make them overlap. Bring them very close so that it's one sign. You can have two be very close tabs somewhere. But it might also be interesting to look at random models, because when you place them just far apart and within the direction you have oscillates, then it's essentially you have the random models, and that's what they use and the others should work on now. We start with the simplest model. The coupling J we look at to be either to favor the singlet, and we call it an antiferromagnet, or we make it favor the triplet, and we call it a ferromagnet. And we will, for now, ignore any of the free particle interactions, but just look at the two-body term.
What is pi?
Pi is the projector of the two particles at sites I and j onto the total singlet state. That's how you can write the Heisenberg term.
So, I'm sorry, I thought that the rub here is actually there is this anionic statistics, which implies some kind of long range.
So we have the particles localized just like in a spin model you localize your fermions.
Yes.
Then when you bring two fermions close, they might hop and hop back and exchange.
Yes.
And if you project it down into the lowest set of states of the localized ones, then what you get as the two-body term is a splitting between the singlet and triplet state.
Yes, but the way you bring it together, that answer depends on the path.
The anions are localized. Now, what are the paths they do? How they hop and braid around, and you have to sum up all those processes. That just gives you then, in the end, some persistence-dependent coupling constant. We don't care where it comes from. We just postulate a phenomenological model. There's some effective interaction here.
So I would believe your answer, but just basically, aren't you losing the notion about the winding together? You can just project to the singular and triplet?
Doesn't that depend on how what the commutation relations of these projectors are?
Well, we look at two particles at first and say, what is the model that I can write down? And the only model is one where I assign a different energy to the singlet and triplet.
Yeah, but when this projector onto zero spin for particles I and j,
Yes.
if I take another pair of particles k and l, which are both disjoint, distinct from I and j, do the projectors?
They commute.
They do commute.
Yes, they do. They do.
So, Mathieu,
Yeah.
are they still anions?
That's the question. What happens? What happens when we add that interaction? What comes out? Are the things still spin in Heisenberg chain once they interact?
So let me ask you this, take a Laplace wave function. Take a Laplace wave function, do the plasma analogy. We have logarithmic interaction, so you know that these guys keep track of each other very far apart.
Yeah. Now you localize them.
I understand, but there's a way to enumerate the incompressibility of the effect of the gauge fields, Chern-Simons.
Yeah.
So here actually, where exactly this Chern-Simonness, or the non-abelian, basically anionic, the notion that actually I can take one anion and drag it around a very large distance around and pick up the phase. Where is it in the interaction?
What this comes in here is that you take the quantum Hall state, you take two quasi-particles, you take them in the total, one of psi state, and then you calculate the energy difference, and that's the splitting. You just have to calculate it directly in your model, in your physical model.
And we should let it go on and it'll be apparent.
And you will just find the difference in the energy between the states. if they get close. Where it comes from, we don't care right now. There have been people who calculated that. A few papers here, and what the sign is depends, as was mentioned, on the distance and on the model. So it's not universal. If you want to do a microscopic model of what happens in this specific device and so on, then you have to really calculate it for the distance in the device, where they're pinned, and so on and so forth, and it's probably random. But we start from the homogeneous system, and we will simplify it a bit further.
Well, can you, I'm sorry,
Yeah.
yes, but the fusion channels, I'm just confused about, can you explicate that more with that, you know, how, when you,
Yeah.
yeah, so what, is this distinguishes the model, or what the fusion channels are, or what,
So
just
this
sign
was,
J,
this is just the sign of J. If the sign is that it's antiferromagnetic, it favors the singlet, or it might favor the triplet, first, or it might then oscillate, so that's complicated. It can be some complicated distance-dependent function, and that's a model one can also study. And we will start with the simplest model, and we'll simplify it a bit further at first. So we take only a model with a constant interaction between nearest neighbors. Constant sign at first. Because we don't want to start with the most complicated model, but we want always the simple models first. And see what comes out. So we have the simplest nearest neighbor Heisenberg model. And instead of having the anyons localized at random places, we at first line them up in a nice chain. So let's first study this anionic version of the Heisenberg chain before we talk about some complicated long-range random interactions. And see what comes out. Now the question is, are these still anyons? What's the phase? And there were predictions about it by my theory and math colleagues, which all turned out to be wrong. In the end, once we showed them the numeric solution, then they said, oh, now that we see the solution, now we know we can solve it by beta ansatz. But they needed that first. So let's look at this chain of anyons. And I don't have much time to derive the full Hamiltonian, so let me quickly sketch how it's done. And basically, one doesn't use the standard basis used for the spins, where you enumerate it in terms of the SC quantum numbers of the spins, like up, down, up, and so on. But we define the basis for the fusion products of the spins. So we have here the tau particle, that's the spin 1/2. Here's the second one. And then that state here, when we fuse two spins, it can either be a spin 0 or a spin 1. If it's a spin 0, then when we add the next spin half, it's a spin 1/2. If it was a spin 1, if we add the next spin 1/2, it can either be 1/2 or 3/2, if the 3/2 exists, and so on. And so the basis comes through an enumeration of all those possible fusion outcomes of the spins. The same works just for the SU2, and then it's just the Heisenberg model in some strange basis. How do we evaluate the Hamiltonian? Let's say we want to calculate the fusion product of these two spins. Are those two spins in a spin 1/2 or a spin 1? What we know is what is the total spin up to here, the total spin up to there. And now we have to use the 6J symbols to change the fusion to get the fusion product of two of those spins. And those 6J symbols are called the F matrices for the anyons, and it simply figure out the algebra, and then it gives us a 5x5 matrix that we can write down, and then we can solve the model numerically. Once one understands that, it takes half a day and the model is solved. Now the prediction was, when you do this, all things just gap out, the anyons vanish, there's nothing left. So we calculated the gap as a function of system size, and we plot here the gap as a function of 1 over the system size, Balansky and by Dimachi, and we see the gap vanishes. And the gap vanishes linearly in 1 over L. That reminds one say this looks conformal. So this could be a certain conformal field theory. And then one can calculate the central charge. And we found that for one coupling, the central charge is 7/10. Then one knows exactly there's only one unitary CFT that fits it. And once one knows that it's 7/10, of course, the first guess was 4/5, but we told them that's a 7/10. Then I realized, hey, when you stare closely at the model, it can be solved by Bethe-Ansatz. And then Andreas Ludwig a month later said we don't have to solve it because it's already in Baxter's book. And what it turns out is that all those Heisenberg chains of the anyons at level k, when you look at the transfer matrix of those, they form, then it's just the transfer matrix of the restricted solid models, which are effectively the static models and the famous minimal models of the unitary CFTs. They are complicated, kind of constructed and fine-tuned the static models, which here are just simple Heisenberg models of anyons. So much more natural, and it can be solved exactly. For the level 2 case, one gets the Isinger CFT. For the level 3, in the entire case, the bracket critical Isinger model, and so on. And then in the limit, when k goes to infinity, one goes smoothly to the standard interferomagnetic Heisenberg chain. And for the ferromagnetic case, one goes from the Ising model to the three-state pods, and then gets the Fermion theories. And all can be solved exactly, after one showed numerically that it can be done.
What does it mean to solve exactly what is actually calculated?
It can be solved by Bethe-Ansatz.
What is the outcome of this partition function? Okay. Wave function.
The whole spectrum is known in the end. And when you then match the spectrum to the numerics, then all the states can be identified with the primary field and the sentence of the CFT, so it's all known. So the matching here, the mapping is nice and works beautifully. What's interesting is that here there's the primary field at the scaling dimension of 1/5 at the same momentum as the ground state. And normally that would correspond to a relevant operator that can open a gap in the system. Here in this model, if we perturb it, the ground state remains gapless. It's protected. And the reason is that this field here comes with a different topological charge. We have this ring of the anyons, and if you want to excite that field here, then you have to change the flux through the ring. And that cannot be done locally, so it's protected, and this here will not open a gap. We looked then at the higher levels, and we looked at the general case of NEK, and we checked it numerically up to 5, and the has some arguments for the high k, that at any level k it stays protected. There is no relevant perturbation at all, and the chain stays gapless when you perturb it. This only is lost in the limit of k going to infinity where the marginal operator appears in the Heisenberg model. And now we have the first realization that these minimal models are just Heisenberg models of anyons. But the next surprise came when we wanted to understand what happens when you couple two of those chains. And then what turns out is that you can describe this critical theory of the chain as the edge state between two different quantum Hall liquids, just like you have projected before. And the gapless state can thus be interpreted as the new liquid formed when the anyons interact. And then we have an edge state where you have the construction that is just this critical theory of the chain.
It's
It's two
two edge states.
edge states, yes.
Yeah, from the two sides.
Yes. Here and here. Two edges. Yeah. And so, when we have, for example, an SU2 level clear liquid, the ground state of this Nachi Chiga system, like in the 12th wall state, meeting at the 5-half, which might be in the Ising phase, and the edge between those would just be this Nachi Heisenberg chain. That's just the critical edge theory here. So that's what we get with one type of couplings. When we change the couplings to be ferromagnetic, then the theory is this here, the Fermion theory, and then it's a cosine construction with some abelian U1 theory, and so the ferromagnetic the action induces the abelian phase, the warring abelian phase inside, and then there's an edge to this non-abelian phase. And that's the ferromagnetic state.
Can I ask?
Yeah.
So what determines the direction of the propagation of edge states? You know what I mean? You have some Hamiltonian living inside. In that Hamiltonian, so what's in that Hamiltonian which tells you which way edge states go?
In this case, when it's just this sliver, there's no direction yet.
Yeah, but you have to have several chains.
This
right?
is achiral. When you have several chains, then the model itself becomes chiral.
Because you have to decide on a fusion path or something? Or?
Yes.
Yes, exactly. Because the liquid is chiral, and so you have two.
Your fusion path will go something like this or around.
But it would seem like all you have is Heisenberg interactions. The only difference from usual Heisenberg interaction, you cut off spins higher than KO2. So there's nothing chiral about these rules.
When you have the single chain in near same interactions only, then it's not chiral.
Once you couple them,
Once you couple them, then you need to take longer range interactions, and then you have to braid either above or below.
But if I take two chains and I
Yes.
one with a fusion path where I go down one chain and then back on the other, and then I could have one where I go in a zigzag.
No, it does not depend on the fusion
It doesn't?
path. It depends on the choice of the braid the phases in the braid matrix.
The phase in the what?
In the braid matrix.
Oh, okay.
When you is that a blackboard here? Yeah. So let's say we take two chains, and those are the anyons.
Yeah.
Now I say, okay, I might make a fusion path like this, for example,
Yeah, right.
and then I let them interact.
Yeah.
Okay, that's easy.
Yeah.
And this means I first have to braid this with that,
Yeah.
this way, and then fuse it. When I take another fusion path, like this,
Yeah.
and I want to do this, then I have to braid it 1, 2, 3, 4, 5 times.
Yeah.
But it gives the same result because it does not depend on the choice of the diffusion path. That's just the basis change.
Okay.
But when we do this braid,
Yes.
we have to pick one phase, plus or minus. And that choice makes it chiral. Because the liquid under there is a chiral liquid. So you have to say what's up and what is down.
So you decide this CR for the liquid you want. This is inside you predict that there should be this conventional superconductor.
There's some conventional abelian quantum Hall state.
But if I take it as one P with conventional.
Yeah.
So what does it mean? It's gapless guy or gap?
Gap. It is gapped with the gapless H. So now what happens when we take multiple chains? And the first tricky thing was what happens when we have multiple chains and they're not even coupled because they are anyons. It changes the spectrum already. And that we could explain using this liquid picture. When we say we have those chains, now we have only couplings along the chains like this. And we get the non-trivial spectrum that can be explained only if we assume that there are these slivers of liquids in between. And then we need to have some matching boundary conditions. And that works out. And now the conjecture was, if we couple it in both directions, won't we just get a big blob of this newly formed liquid surrounded by an edge? We checked it numerically, and that is just what we saw happening. When one looks at the spectra, that's what happens. The key difference is when we take a system like this, for let's say a 3-leg ladder with standard spin 1/2, which is gapless. When we make it periodic, it remains gapless. Here, this system, when we take this and this gapless due to the edge, when we make it periodic, the gapless modes vanish and we have a gap opening. We looked at the degeneracy of the ground state, and it was just what the liquid inside predicts. So we have numerically evidence that that's what happens. When you take a 2D system, then it forms a new quantum Hall liquid inside with an edge around. That's one case that can happen. The other thing that can happen, it might just all vanish, it might just tear up and vanish, and you get the original liquid back. So you either have the outside blue liquid and the anyons vanish, or you get a new quantum Hall liquid also in the ground state without any anyons.
So the orange here or yellow means exactly this trivial U1.
This out here might be SU2 level 3, and in here that might be SU2 level 2. Or U1. Yeah.
So how sensitive are these results to tiny changes in the model? Let's say, assume it's all antiferromagnetic, and then I move one particle a little bit, and it becomes, let's say, ferromagnetic in some local region.
Okay, let's first move a little bit that the sign doesn't change, and it's just from this order that nothing changes because it's a gap model. If you move it so much that the sign changes, then we get a random coupling model, and that's what the group of David Hughes looks at now. The results are not here yet. It seems that it moves to. I don't remember the latest result because there were some bugs in the calculation at first. But in one case it runs to a you have the strong Balatsky fixed point, and in the other case it runs just to one side of the couplings. But that's not finally solved yet. When you move the bit and signs change, that's it's an interesting problem being worked on.
Just recall that you don't need to move that far. So in all cases, you basically it's
Yep.
I don't know. For a B-wave superconductor, just Fermi wavelength that
Yes.
you move it.
You move it a bit, the sign changes, you get randomness, And when you then get out the strong couplings and some G treatments, the signs start to mix.
How is it possible that interaction changes sign when you move it from certain wavelengths in P plus IP superconductors if there is a characteristic scale which is psi?
Because in what score there are a lot of Fermi whales.
But if you're far away, if you're on the distance much larger than the psi, you don't know that.
No, it's exponentially small with respect to psi.
Oh,
but there is an overall factor which multiplies by psi.
Oh, I mean, the exponential factor is there, right?
Yes, it's there.
Okay.
So what happens when we take two such chains and couple them, that the inner, the edges are coupled, get out, and we get one edge. What happens sometimes, depending on the width of the system and the coupling sign, is that both edges get out, then it's just the blue liquid left. So and that fits nicely to some of the previous work on the Majorana fermions by the Ried and Ludwig, and by the Grossfeld and Stern. And here actually, if I remember correctly, the sign doesn't really matter much for the final state. And it also works well for the work by Grossfeld and Schoutens on the edge between the Fibonacci and the Ising theory. So the way we view the interacting linear systems is that when they interact, they form some new state inside, some new quantum the liquid with an edge state around. And now one could argue what happens when we start from a quantum Hall state. We start in the middle of the plateau and we dope it away from the center. The anyons move closer, overlap, start to interact. And if we now ignore randomness, they would form some new quantum Hall liquid around, less than 1 billion. So as we dope away and the low temperatures, the state becomes less and less than 1 billion. The low temperatures and the ground state would just be in a billion state. Which state it gives us might depend on the sign. It might be different for the quasi-particles than for the quasi-holes. And the next step is, of course, to look at randomness. So what we've seen is that 1 billion anyons can support quite well the variety of states. We looked at the Kepler states here with edges. There's much more work we did. One can look at the longer range couplings, adding the J2 term. One defines the eccentricities as in spin chains. We find the Machum de Gauche point, for example, gap phases, gapless phases. One can look at the spin 1 chain. One finds the Haldane phase. One finds a generalization of the T point and more. So essentially, you can take any of your favorite spin model, make it anionic, and write a new paper about it. Look at randomness next. Look at higher spins. Make them mobile. Make a T-chain model of anyons, and so on. It can all be repeated. If you think this was exotic, this was just the start. We can make it more exotic. There are the non-unitary anyons. that give rise to seemingly non-Hermitian models. One can solve them with great ansatz. The spectrum is real, although the Hamiltonian looks non-Hermitians. They are the edge states between non-unitary quantum Hall liquids. The big question is whether those models can exist. Can it be an effective theory for some physical system, just written in a non-Hermitian way? The answer is we have the work in progress where Dr. Mike Friedman has an argument why these non-unitary theories cannot describe any physical quantum Hall state. So this is a bit too exotic, this is non-physical, and so I'll stop here.
Questions?
Yeah.
Well, you have the chain of anyons.
Yes.
When you talked about the superconductor initially, could you sort of make a row of
It would be
pinning sites or something?
It would be a row of pinning sites for the vortices, yes.
Yeah.
Correct. Yeah. That's how you could build that chain. Finely tuned, of course, to make the coupling all linear.
Yeah.
Or for the chain you can do the random chain based them randomly, and there was some work on that with the Raphael who looked at the strong randomness fixed point in this 1D the random chain, and that's understood. The 2D random case is not understood. The 1D is.
So when you think say randomness, you just assume that you have random couplings.
Yes.
So those sort of would be just a case that you don't actually have regular leading crystals, but
Yes.
the separations might be.
Yes, might be a little bit different, but it's exponential and the sign fluctuates, so it's immediately quite random, and it runs into a strong randomness fixed point then, and that can be solved. Yeah.
I'm sure that it's a direct concern to this talk, but this oscillations of sign.
Yes.
First impression is that it is mean field result, and as such, it is a, how do you know, I don't know how to say it in English, excess of accuracy. So basically, you cannot calculate such a, with such an accuracy, which is plus or minus 1 in mean field.
Yeah.
So in quantum fluctuations, will smear all of this in a field repulsion.
So that's why it's better if you want to.
Sorry? Yes. Yeah. These oscillations will be zero, but it will be kind of conventional repulsion, as in usual superconductors. Would you agree with this?
I would agree that this is at a very, very, very low scale, but we did estimate what are the scales in the quantum Hall case, at least. In the quantum Hall case, when you get them close enough, you can realize it at about the millikelvin scale.
How do we estimate it in the quantum Hall numerically?
Yes. So when you can bring the couplings up to about the millikelvin scale when you bring them close.
But there's no
Now,
oscillation.
I'm not saying this is a realistic model which we will build in the lab this decade. Right?
For instance, like voltage. There's a comment on that. So I've been working on this honeycomb lattice model, but they're also, even though it's sort of a theoretical model, it's not really like the working professional quantum Hall liquid. There you can sort of define vortices, which are like the anyons, and you really have conserved quantities, which really pin them down to certain positions. And then you can study like that as a function of the separation.
Yeah.
There is, you can actually find this oscillating as well also. And then these are like statically pinned down. There's no fluctuations about positions because of the complete theory.
I didn't refer to fluctuations of positions. What I was saying is that if you are in weakly coupled GCS theory, and you calculate in mean field, in framework of mean field, you may get it. However, everything fluctuates. Modulus of delta fluctuates. As modulus of delta fluctuates, this levels inside the core also moves up and down, and all of this. Anyway, so calculation, so mean field is defined with the precision square root of number of electrons, right? And this effect comes from just plus or minus 1 electron. So that's what my guess. That's what my. Let's put it. This was a question.
Maybe I don't understand where you think this oscillation is coming from. If I see, if I understand it correctly, if I look at the lattice of vortices in a P-wave superconductor in BCS, and you ask about coupling of these Majorana states, they just form a band, and the sign doesn't change.
No,
they just
it's
pop.
two vortices.
You look at.
Yeah, but the vortices repel. It doesn't. That does not.
You look at two-pin vortices and look at what is the energy of the two states as a function of distance.
Sure. So you're asking
And it,
about
and it oscillates.
And this energy also. So the one given oscillation.
Yes, that goes like this and then vanishes.
But that oscillation is of the overall. Is it important whether that oscillation, does it matter if the Majorana state, the two Majorana states are filled with a fermion or not? If it doesn't matter, then it doesn't come into
It comes from all states, not only from zero level, but from all of them. When you integrate, it's like in the multiple oscillations. Yes.
Yeah.
You start with two Majoranas that are separated, and one Dirac, so that can be
Right,
occupied or unoccupied. Now you're asking, what is the energy of occupied versus unoccupied as you bring them together?
Yeah.
Is that so obvious that it doesn't oscillate?
No,
They change up
one
there.
is minus the other.
What?
One is minus the other.
One is minus.
Minus the other.
Okay,
No, but it changes.
So they change.
One positive is the energy for occupied positive or negative?
Well, if you bring them very close together, the energy for occupied positive, for empty negative, but as you take them apart, they oscillate. I mean, in opposite. Well, one of them is minus the other.
So my claim is that it's a filled state.
That might be true.
Yeah, sure.
Yeah.
But once you go beyond it, all of this will smear to zero. This is a guess.
When you go to lower temperatures, something will remain.
You can always make it.
But there is integrals there. There is a full band which is filled with this, right? It's not only zero energy. So
There will be some remaining effective interaction at the
that's
end.
my guess. If you want to bet.
So, in case you're right and it just averages out, then that's great news for the quantum computers, because then it will be very easy to build them.
Yeah, I mean, I would like to help.
Even better. Okay.
Questions? There's a scientific.
That's not my pointer. It's from here.
So there is a change in schedule, right? I don't know if you're aware that Vincent is not feeling well, and so there was some adjustments.
Yeah, so you're the last talk.
I'm the last talk, yes.
As we lay our hands on our pillow tonight, this will be talking to That's it. What'd you say? What's he reading then?
Well, okay, let me start. So, I'll be talking about Dirac materials. My name is troyer+balatsky, and so this would be somewhat of the introductory talk, since Igor asked for quite a bit of introduction. So I would like to introduce some new concept here, and the concept of or notion of the Dirac materials as a class, and I'll be pointing out similarities and differences between different compounds or materials, but there are some significant and meaningful similarities that I would say warrant to call the certain class of certain set of materials, unify them into the notion of the Dirac materials. Obviously, it does make sense if there is one or two of those oddball outliers. But if we as we go forward, we discover more and more of those. I think it's a time to acknowledge the similarities, which could lead to very powerful predictors or useful predictors. Now, the way I'm going to highlight the similarities is by using the notion or by using the tool or device of response to local perturbations. Okay, so I will just say that once we have a Dirac material, we can have a few of these reasonable predictions about the response to the local defects. And so as an example, I will talk about the local scattering of these charge impurities in the cuprates and the graphene. And then it allows me to expand it and use this local scattering as a tool, as a test to check the stability of the topological insulators. Now, as everybody, we've heard a lot about the protection, topological protection of topological insulators. So what does it exactly mean? And as a simple tool, I will just investigate the response of topological insulators to local defects. And then actually I will show you some preliminary density functional calculations and argue for the impurity states of how it relates to the gap opening for magnetic and non-magnetic impurities in the topological insulator. So here's a set of people. I just want to acknowledge very useful collaboration or interactions with Mike Romy, Hari Manoharan, Hanaguri, and the relevant work in this context is done by Rudra Biswas, Tim Benning, and other collaborators. Now, I'll be talking about Dirac materials, but since it's, I was asked to do a pretty broad introduction, let me start with the Dirac equation. Let me get the off the chest right away. That's a very important equation. It certainly has a predictive power. And Dirac wrote a paper in about 1928. And he was concerned with the relativistic invariant Schrödinger version of Schrödinger equation. And he realized pretty quickly that he cannot do it in the conventional way, so he was forced by the Lorentz transformation, by the need to respect the Lorentz transformation, was forced to write the equation that has a linear power of P and T, and therefore he had to go to matrices. Now, in itself is actually an interesting mathematical device, but what it means is that this matrix as an operator is applied to the spinner, and the spinner has more than one component. So inherently you have an object where you have at least two entities, two entries into the spinner, and he actually conjectured or posited that one of the components of the spinner describes particles, and another one describes antiparticles. And so in a way, basically, the prediction of the antiparticles is not the consequence of any sort of deep math, or maybe it is, but basically you can see it from the fact that you already kind of make this leap of faith of writing spinners. So you have a two-component operator, two-component object, and that codifies behavior of particles and antiparticles. Okay, so he got a Nobel Prize pretty soon after that. For us, in the condensed matter of physics, I think it's relevant and important that this equation, like I said, has a predictive power in terms of antiparticles, but it also governs our intuition about the behavior of spin-Monk-Hall particles in magnetic field. It leads to all sorts of Zitterbewegung and Klein paradox. It is very useful in understanding the role of spin-Magnetic coupling. Okay, so here is antiparticles. Particles and antiparticles created in the chamber. Now, so with that, actually, I wanted to switch on. So Dirac equation is very important. I'm not anti-Dirac equation, but I'm just saying, actually, when you apply this Dirac equation to real materials, it matters, actually, what kind of material you're looking at. So there are similarities, but there will be differences. And so let me do the kind of two-step introduction to the Dirac materials. First, let me start with the low-level one, or simpler one. So let me say that if I have fermionic excitations, or material that have fermions, then I can look at the excitations about the ground state, and if these excitations have a spectrum that has this linear dispersion, that leads to sort of immediately some sort of unexpected power law dependencies that go beyond or outside of the standard Fermi liquid. For instance, specific heat will go at a higher power of temperature. If the materials are superconducting ones, that there are temperature dependencies and penetration depth, there are the temperature dependencies, unusual temperature dependencies in conductivity. And So here's a cartoon, for instance. You can think about this like having some lines of nodes or points of nodes where we have the soup of fuzzy particles lingering there at lowest temperatures. That controls a lot of the low energy response of this material. Now, so basically, it's been sort of discussed quite a bit, especially as we go forward about the design of the materials around being clever. I would say that most of them are discovered serendipitously, but if you sort of want to discuss how exactly we can build or develop the Dirac material, a couple of ways I see. Maybe there is more. And in fact, actually, Victor told us about something like time dependence, so like non-trivial state in the steady state generated by applying some time dependent fields. But at least sort of in a stationary way, I see that there are a couple of ways. One of them is a trivial one. Suppose I have a, well, it's almost irrelevant what the reference state is. Suppose I have a metal, or I have a semiconductor, and if as a result of some interaction I cool it down, and there is a novel state sets in, for instance, some ordering state that results in the gap in the fermionic spectrum, then this gap, in case it has nodes, implies that it's actually at lowest temperatures. I will have the picture something like this. I will have either lines of nodes or points of nodes if the gap is non-trivial. An example of those collective states with non-trivial gap structure in Dirac fuzzy particles is the helium-3 superfluid, heavy fermion superconductors, possibly organic superconductors, high DC, and some density wave states. Now, there is another interesting way to develop these Dirac materials, and this is actually given us by nature, essentially at the band structure level. So we have graphene, and now lately also people talk about the topological insulators as another example of the Dirac material. So the last but not the least, again, it's not about the equation, it's about real material. Now, so a little bit more elaborate way to describe what I mean by Dirac materials is that suppose I have a Brillouin zone, I have a nice pristine clean material, I have a Brillouin zone, and I have propagators, Green's functions. So then, for the simplicity, I look here at the two-dimensional metal, and I'm saying actually, let me execute the search of the poles of the Green's function as energy goes to zero, namely to find out the region where I have particle-hole excitation that costs me the least energy, zero energy. Okay, so I will build up this set of points with this zero energy particle-hole excitations. Now, in the case of Dirac material, it's true also that I do have a particle-hole excitation that I can excite across, if you want, the Fermi surface or Fermi point, and it all holds together, except one important difference, and I think it's a defining difference, is that the phase space, the dimensionality of this 0 energy states, is at least one less for the Dirac. So it could be lines of nodes or points of nodes. Now, if the conventional Kohn-Sham or whatever this band structure tells us that, for instance, two-dimensional metals should have a line, and I'm ending up with a point, it's clearly not the general case. It means that there is additional organizing principle at work, and also there's additional symmetries that actually could happen at either the level of the band structure or the level of the disordered state that are at work that are basically allowing this unusual crossing point. So put it differently, actually, if I have a crossing point between two bands, typically what happens is that actually there is avoided crossing and the gap opens up. And it's only basically this point is protected if there is additional symmetry that holds it together. Okay, so you can say from the outset that if you want the phase space or number of these Dirac materials will be much less and fewer. But basically, then it means that if we have some general statements, they probably have a very good chance to be pretty universal. Now,
if you take into account exciton type interactions, then this crossing point is unstable.
Well, so I can see already there are people in the audience who are disagreeing. It depends. But basically, sure, there is a hammer big enough to destroy everything. And so if there is interaction that's big enough, it will pop up the gap. And in fact, I will argue the same for in a somewhat different way. I will argue that topological insulators respond to, in a more conventional way, to the strong impurities. But let me just start slowly saying that if I have a big enough interaction or no disorder, that's what will happen. Now, why bother? Why it might be interesting is because if I want to look at the functionality or functional response of these materials, it's much easier, for instance, if I drive by some interaction, as Victor pointed out, gap opening at these direct points or lines, it's much easier to open the gaps in the fewer points than everywhere on the Fermi surface. So that's good. Actually, it offers some hope of greater degree of control. Another interesting point here is the dissipation, lambda density here, would be much less. So if I'm really serious about electronics based or optics based on these Dirac materials, it probably will be inherently less dissipating. Now, so like I said, actually, I will from now on switch from rather general to like a scaling analysis of different responses to very particular case of effects of defects. Why? Well, number one, actually, I find it interesting. Number two, I think actually what happened, there is interesting switch into logic actually when we discuss the properties of quantum properties of materials. This laptop, this projector, this laser work precisely because I have a semiconductor which in itself, without engineering, is a dumb, actually wide gap semiconductors. And so the functionality of the device and the non-trivial response only emerge as a result of engineered band of the impurities or dopants. And so impurities actually are very useful also from the point of view of functionalizing the device, and in fact, or materials. And in fact, the phase space of the useful materials with impurities of some sort, or dopants, is much wider. Okay, so it's not only that we want to look at the pure quantum states, but we want to look at the pure quantum states in the presence of some defects. Then, well, of course, you know that due to the, that's what I said about the semiconductors, with the miniaturization of the small devices, I think we're coming to the point where it could be sort of in transistor, one or two or very few dopant atoms, in which case the standard continuum, so like lifetime, average lifetime description would fail. And last but not the least, actually, we certainly have now the tools to see those impurities one at a time. It's like a keynote talk about average salary of the people sitting here. That's one thing, but talk about the range of salaries and the specifics of this, and everything else is very, very different. And so that's what will happen with these discussions. That now that we have right set of glasses to see these impurity states, we can see them one at a time. We don't have to talk about average. And then, as Matthias already showed us, there are suggested very interesting schemes for the quantum computation that use or utilize deliberate perturbations and manipulation of the defects or states at the nanoscale. So let me move on now to the case of a given superconductor. As exhibit number one. This is a real image of impurity. So the central piece here is this copper oxide plane. So material itself is complicated. But we believe that the crucial piece for high DC superconductivity is this copper oxide planes where electrons leave predominantly the holes. And it's made from the d orbitals of the copper and the p orbitals of the bridging p orbitals of the oxygen. And so in some low energy sense, I can think about it as a Fermi surface. And then I come in and cool material or the superconductor to low enough temperatures. I open up this unconventional gap, which has its D-wave signature. It has a plus plus, low and minus minus. Okay, so if I write down the Gubagalin-Bogdajan equation, I have diagonal piece, which is a quasi-particle energy. I have off diagonal piece, which is a gap. And because I need to go from plus to minus while keeping the gap real, there will be points along this two-dimensional Fermi surface where the gap vanishes, and at the same time, at the Fermi surface, energy vanishes. So basically, there are set of four nodes in a D-wave superconductor that is a source of all sorts of infrared or low energy physics, which is very, 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 very interesting. A number of people here in the audience spend time looking at those. So all I'm just saying, usually, you can view it as a pathology because it doesn't give you a full degree of protection, for instance, not the full gap state, but at the same time, you can view it as a very interesting piece of physics. Now, one question we not only asked, but people were asking actually early on was that what happens if I put one defect in a superconductor? Now, it's known that actually the superconductivity will collapse, will be killed, destroyed if I put defects in, be it magnetic or non-magnetic. But the question is actually what happens if I have only one? Clearly, one impurity in like a 1 cubic meter of superconductor won't do much on average, but locally they can do a lot of damage, right? Because I know eventually I have to come to the point where the total superconductivity everywhere is killed. So the way it's killed actually is very local, and what happens actually if you put defect in, say I put here impurity, scalar impurity with potential U, and I image locally what electronic changes are, a couple of things happen. In fact, actually the same thing happened, but it has a few different features. Number one is that what you start seeing is actually these coherent peaks coming from the D-wave gap with the field in due to this nodal gap structure, field in states. There is one additional resonance comes in. So it's actually, it's already, if you want, harbinger of death of superconductor, because if you keep doing it, you will have more and more states pulling inside, and they will fill up the gap, and the superconductor becomes normal. And in a way, basically, every course of Gorkov discussion about the gapless superconductor is a kind of pre-tipping point or pre-tipping state of the superconductor where all this impurity, the resonances fill up the gap and make it gapless. Now, what's interesting is that the position of this resonance is inversely proportional to the strength of impurity potential, which is very unusual. The harder I drive, the more and more this level moves to zero energy. Another sort of more interesting or more exciting proposal at the time was that because I have a gap, and I have an intragap state, I have like a state inside the potential well, so this gap works as a retention wall. It basically confines my state near the impurity, just like I have water in this cup. But if I have like 4 nodes of the gap, the water will leak out in the fashion basically. So you can solve the problem of the localized impurity state. You will see that it has a 4-fold Taylor states emanating from the nodal directions. And so the proposal was at the time that actually by looking at the electronic states near this impurity site, you can guess or infer what the pairing state is because you can measure the nodes of the gap. Now, the fact that those are not, well, they were at the beginning simple theories like constructs, but it turns out that, like I said, if you have the right glasses, you can see them. So here is the case of the local STM measurement. And I'm not going to describe what STM is, just a local tunneling conductance probe that could be so like very precise in terms of lateral resolution up to angstrom scale. What you see is that locally it produces impurity-induced resonances. So this red line is the tunneling right on the impurity side, and the blue line is tunneling away from the impurity side somewhere out here. So this is number one. And number two is actually intensity of this. Yeah, this is a real space image. So if I keep my bias at this value of about sort of near zero, it's not exactly mid-gap state, it's intra-gap state, but not mid-gap state. I'll see this intensity as I move around. Because it's a Dirac fermion, the tails actually will decay as a power law, and there is very simple sort of power law prediction of how it should be decayed, like because it's a Dirac propagator in 2 dimensions, and the tunneling conductance, albeit back then when Eric Hudson measured it, he had to angle integrate it to get enough signal to noise, but within the range of about 0.8 to about 2 or 3 nanometers, it does decay as a 1 over R squared, as the theory predicts. And then with the same sort of strength of parameter U, you can fit reasonably well the position of the peak and the width. So the dashed line here is the theory, solid line is experiment. And you can see that actually if you fix the position of the resonance within a factor of 3, you're getting the width. Now, so I'm going to build up on the same theme again and again, basically. So then let me take graphene and ask what happens if I put defects in graphene. And people come to this discussion from many different angles. For instance, from starting from the quasi-classical or smoothness impurity potential. I will just look at the very localized impurity, in which case pretty much all the symmetries that are present in graphene are broken. Well, I presume I don't have to talk much about what graphene is. Graphene is graphene. You've heard a lot about it, okay? So then, so the idea is to use a defect, and in this case we put very strong impurity potential right on this side, or we can have a couple of them, and see the same story actually, what the response of graphene would be to these impurity states, or to the impurities. And sure enough, what comes out is that the story is very similar to what happened in the D-wave superconductor. I have an impurity sitting here, so this side itself works as a unitary scattering center, which drives the wave function of electrons around, carries around to 0. So on the impurity side itself, there is very little intensity. Say this is the A sublattice side of graphene. But you can see that actually there is a low line, low energy state at about 0.1 electron volt for our parameters, which has two features. One, it has this Friedel oscillation, which is fully commensurate with the lattice. So we looked at the Hall-Field case. So you see if impurity sits on the A sublattice, B is bright, A is dark, 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 B is bright. So you have a ripple. If you sum all these ripples over the total field states, you get what you know from the textbooks as a Friedel oscillation. But the advantage of STM is actually you can do it one at a time or at a certain energy. And that's how this localized state looks. It has envelope, it has beating, which is, in this case, 2Ki. And so I agree with whoever was discussing this issue in the superconductors. The same story will happen there. If you have a P wave, it's a little bit more complicated because there will be some nodal directions, but overall there will be Friedel oscillation, and you can solve it in an A-canal approximation or whatever you want to do, but there will be some kind of part that dies over the gap, and there will be leftover part that goes as a tail.
Yeah, but here it's a simple particle problem.
Oh yes, for P plus IP is fully gapped, sorry. For P.
Yeah, no, simple question is here. Why do you consider that impurity is on the side there? It could be in the center of the cell too, and then probably the profile will look completely different.
Yeah, so we have answers for all of them, I just. Not for all of them, I cannot do it for all of them, but we certainly looked at the, so just since you brought it up, you can put impurity in the middle, and in which case, especially for the Conde effect, there is a very interesting Berry phase cancellation of contribution, which drastically modifies the Fano factors for the Conde problem, compared to the cobalt on the copper. So we put in the middle, we put in the vertex, and we put in the middle of the bond.
So does it correspond to doped graphene or
So right now I look at this problem with exactly how field case is commensurate. Then if you move off, the beating will be slightly incommensurate compared to the lattice.
PF is non-zero?
PF is 0. It's exactly at the point. It's a how field case.
You said you have Friedel oscillations with KF. If it's 0, so what does it mean?
Well, it means that this is a Friedel oscillation consistent with the side of the brilliant zone. The point is K capital. And so when it's not the KF compared to the center of the brilliant zone, it's a full K. So if you create a wave packet sitting in one node, it still knows about the total wave vector. But then when you feel it, it will have kind of harmonics at K plus minus, K capital plus minus K Fermi.
So you're considering only magnetic, non-magnetic impurities involved?
Where?
Here.
In the graphene case?
Yeah.
Both. And so, yeah, I'm not going to show you the electronic solution. I'm just showing you the pictures since it's like so late. But what happens actually, you will see. You can back out from my discussion topological insulator what happens in graphene. Now, the analytic formula looks pretty well. I mean, works pretty well. So, not that anybody has the ability to tune impurities by putting them with different U. But all I'm saying is analytically for this Dirac response, it will be the same energy, or the impurity will go like 1 over U. Now, so it happened actually, it took them a while, but they looked at this is a PRL published in March of last year, of 2010, where they looked at the irradiated graphene and knocked off one carbon atom with ion radiation. And what they produce is, you can see inside this V shape, if you tunnel away from impurity side or defect side, you have this sharp resonance. And if you go along this ridge, which is shown here, you do have this beating with the right wave vector, but on top of it you have the overall envelope that goes like a 1 over R squared in the tunneling conductance. All right. So I'm going to point out something very simple. And so we're going to solve the kind of impurity problem in the graphene and D-wave superconductor graphically. So if I have a simple metal, and by whatever fiat I created this supposed density of states, which looks like a V-shaped density of states, of the bandwidth W. I want to look at the effect of the impurity scattering, and I want to go beyond the boron scattering. Now, why it's important to go beyond boron scattering, as you know, the boron is incapable of producing new states or resonances. It's only broadened the existing states. So any discussion about the effect of disorder, where you stop at the boron, is equivalent to you coming in and just putting in the lifetime. But if you go to the multiple scattering, you're getting new poles and new bound states. And so this boron, basically, if I look at this weak scattering, so like if my potential on one side is U, then in the weak coupling it would be just U. But then if I look at the impurity side, for instance here, and I come in, scatter, and then come out, and then for some reason come back, and I do multiple scatterings. Basically, I will reassemble these multiple scatterings into this Dyson denominator, and in fact, the whole game is actually coming from the denominator. So the blow up of T matrix, that's how I want to measure the effect of defects, signifies basically the increased dwell time at certain energy, or essentially formation of the bound state near the defect. So the rule is actually, the game would be that I feed in U, and I'm looking for the certain frequency that satisfies this equation, the denominator is 0. Okay. Now this actually, just as a caveat, you can do the numerical solutions, you can do fault self-consistency solutions, you can do it basically in the real space, you can do it K space. I just choose this one because it's graphically points to very simple, essentially universal statement, which can be verified in many ways. So before I go into fully solving it, let me point out that this is density of states, which is the imaginary part of the one-side Green's function. And so attendant to it, there is a real part. And the real part is shown here with this dashed line, yellow. So every time I have a sharp edge in one of the Kramer-Kronig partners, the imaginary part, for instance, has a step, and the real part will have a peak, and it will have some bend here. And inside this notch, it will have this marginal Fermi liquid. The imaginary part goes like absolute value of omega, but the real part will go like omega log omega. For those of you who remember marginal Fermi liquid, so like susceptibility statements. Now, I'm coming in with a very large U, so I'm drawing very low line, horizontal line, and I'm seeking where both real and imaginary part conspire to satisfy that this horizontal line intersects them at the same time. Now, number one state you can see right away is actually for very large U, I have anti-bound state. This is like an upward Hubbard band state. If this state is pushed outside of the continuum, and the larger the U is, i.e. the lower the line, the more and more toward the right my anti-bound state will move. So this one behaves as our conventional intuition would predict. The harder the impurity is, the higher energy state it generates. So this crossing point here shows that you have much more of imaginary part in the solution than the real part. Namely, you have a resonance inside the very nice high density of states continuum. And so this solution will be very broad and relevant. And then actually this is our impurity state right here, which is forming as a result of the following. So you have imaginary part inside this notch goes like absolute value of omega, then but Kramer-Kronig you get the real part going like omega log omega. And so you solve this. Omega log omega is equal to 1 over u. You iterate, you get this. It's very simple. Now, this and this are Kramer-Kronig relatives. So this one knows about this one and the other way around. It's only because I pulled the density of states here that there is a little spillover effect. Okay. So what I showed you is actually in the theory and an experiment. In fact, you do see the reasonable response. I have a Dirac-like distortion and defects produced inside it. These resonances, localized states, or nearly localized states, or nearly localized, or localized nearly states. Those are scattering states, but they produce this pile up of intensity, which is localized. It's not moving anywhere. It's like a pile, sand pile on the beach. Now, so that's fine. It's interesting, but let me now apply this intuition to topological insulator. And so what I want to do now is to say that if I put defects in topological insulator, how protected the topological states are. And the running ahead in the conclusion, I will just say that there is no such thing as unconditional protection. It always boils down to whether energetics of the protected state is favorable or less favorable than unprotected state. And so that boils down to the statement that there is a hammer always big enough that can destroy it. Now, why it's important is precisely because perhaps in this discussion about topological insulators, we'll be moving on from the first kind of honeymoon phase into more realistic discussion about what's really happening with these materials. And that's my message, actually, that one has to look at the data more precisely and try to understand what the response of this material would be to the magnetic and non-magnetic impurities. Now, what we see is that this is data taken about maybe 6 months ago. As cooked bismuth 2 selenium 3 the topological insular, and we can see already these very similar patterns to the ones I was showing you before. So those are the defects, whatever they are, that are not deliberately placed. They come as a result of sample growth. So at this point, they don't know, namely sample growers or the experimenters, don't know whether this is the magnetic or non-magnetic scattering centers.
I mean, I thought in all these materials, it's, you know, the existence of a bulk gap is still not well established.
Thank you. Yeah, I don't want to be too negative, so I guess let's leave the bulk gap outside. But that's absolutely true as well. There is a quite significant crosstalk between the bulk and the surface.
Yeah, bulk gap, then you know, I mean, that introduces another complication, I guess, into the.
So as a band structure prediction, the bulk gap, I would say probably if they do it right, will eventually come in. In the sense, actually, there may be some substitutional or interstitial defects that are essentially self-doping that could mess up the gap. My question is actually, suppose I even given the nice, well-cooked topological insular, if I basically put it in, put the leads in, and have some defects or some impurities sprinkled on it, what will happen in the surface? So I'm not going to talk about the bulk.
If there is a bulk gap, and if your impurity is non-magnetic, I would say that from the general theory says that it's impossible to generate low energy surface states. Right time reversal invariance, or you need to close the bulk gap.
Yeah, so let's see. Yeah, basically I kind of agree with the statement in general, but my point is, well, this is exactly where I'm going. I will just argue that actually if we have enough of the scattering locally, that will engage the states outside your Dirac cone, then you don't have to respect the time reversal. I mean, you form the bound state or quasi-bound state. I see no evidence for the protection. So I kind of, in a way, let's just see. Basically. Let's go on.
Bound states, if they appear, they have to appear at energy scale of the order of bulk gap.
No, it's not. That's the whole point actually. If I have an impurity strong enough that deals with the U, with the spectrum way outside of this protected Dirac cone, my U could be electron volt. My impurity resonance is generated at the energy scale of 1 over U, but nevertheless it inherently talks to the energy, to the states outside of the Dirac cone. So I don't know exactly the full answer. Let me put it out as a hypothesis, what will happen. And I'll show you some unpublished data. So this data is published actually. So something is happening here that generates at low energies or near the Dirac site, generate these kind of bright intensities.
Well, sure, but there are extra complications with materials. Because you see, you can also try then to apply this to simpler system, just to integer Hall effect, which has H states.
Okay, so let's do this. I will
impurities all the time.
This is exactly the. Can you bring up this question exactly when I talk about the H state? We'll just discuss it. A little more. In other words, you're hitting right on the central issue, but I just want to move a little bit forward. Okay. So let's recap what topological insulators are. In a way, basically, it would be nice to have Joel here. He would keep me honest or keep my feet to the fire. But so the way I would sort of use it, I will just follow the Hanaguli's slide or discussion about this. So suppose I have a two-dimensional metal. And the way I can create out of the two-dag insulating state is by applying magnetic field, in which case I have lambda levels, and if my chemical potential is inside, then in the bulk it would be insulator, but there will be sort of non-trivial edge states coming, of course, from the skipping orbits of the electrons. And so the notion actually that topological insulators are the ones which have non-trivial gapless states. So we have this chiral fermion mode that propagates in a certain chiral fashion. And as Victor pointed out, if I have a defect, what happens in the case of a defect scattering, when I'm coming into the electron, basically it just keeps around and moves on. So the crucial piece of the protection of one-dimensional edges in the quantum Hall is actually you suppress the backscattering. There is no backscattering at 180 degrees. Now for the two-dimensional scattering problem in the topological insulator, I'm going to argue that you don't have a suppression of 182 degrees or 179. So you punch out in the scattering integral, if you want in some way, punched out, they just measure zero number or place. You know, it's support of the exact zero is just zero. So in a one-dimensional case, this protection is unconditional because there is only forward scattering and backward scattering. You kill the backward scattering, there is nothing else but moving forward. But if you move this impurity out here and you so like say that actually you can come from another angle, scatter from some from the edge of the sample and come back, basically, you certainly can have it come back. And that opens up the possibility of these multiple scatterings. So let me move on to the. So the way to arrange for the time reversal invariant, if you want the time reversal invariant non-trivial insulator state, is to say, suppose I have a spin-orbit coupling that is clever enough to sort of force my C effective field, which points up, for instance, for spin to the left and points down for spin to the right. Namely, that actually, if I have two spin species, they see opposite values of magnetic field. They both do the chiral motion, but in opposite direction. Then the net magnetic field applied to the sample is zero, and I have two counter-propagating edges. But because of the strong spin-orbit coupling, actually, my scattering from one side of the branch to another one is exactly forbidden. So the back scattering is forbidden. But this is all true, like I said, actually for one-dimensional case. And in the two-dimensional case, one needs to solve the, if you want, multiple scattering problem. You cannot argue presence or absence of the intergap states based on the Born scattering argument.
Well,
Sasha, isn't it the case that if spin orbit's scattering length is shorter than the elastic scattering length, there is anti-localization in the zero conductance is guaranteed in the vector world?
Yeah, so that's okay. So let me qualify it, since you keep doing this. In a way, especially it's my concluding slide or pre-concluding slide. What's really going on? Of course, there are protected states, but what happens actually every time you put a strong impurity, I think actually what happens is the guys basically whatever the degeneracy is of the sheet of two-dimensional protected state is, it jettisons one, let it localize, and actually it goes around it, and the rest of it, of course, does provide this E squared over H conductance. So I'm not arguing that actually the E squared H and anti-localization and other things will not happen. I'm just arguing that actually something has to give, nevertheless. That there has to be some spectral weight redistribution to provide this kind of these bright spots I showed you.
You agree that conductance will, resistance will be zero at zero temperature because that's anti-localization.
Right, right. So those are the kind of the localized states, but somehow or quasi-localized states, but they will not contribute to the transport. Okay, so this Dirac cone with the assignment of the spins was beautifully demonstrated by a number of RPS experiments by Princeton and Stanford groups, and that's the material we're talking about, bismuth selenium-3. Here is the Dirac cone for the calcium doped one, where they hope to put the chemical potential close to the crossing point. Bismuth chalcogenide is here, and it's a more complicated one because Dirac crossing point is sitting near the continuum. So it's kind of like much more challenging to separate the contributions from the Dirac and non-Dirac states. And as we've already discussed, basically the suppressed backscattering as an input in the calculation for the T matrix is certainly there. You have this kind of cosine 2 theta dependence of the backscattering amplitude, which vanishes exactly at 180 degrees. But this is a non-trivial function of angle. It's not zero everywhere for all angles. Now, so then like I said, actually, you do see them and they're pretty ubiquitous. So those are not the deliberately placed impurities, those are some kind of defects that are coming as drawn. I would say also why it could be also a spurious effect of the samples, although I don't think so, but just as a caveat to be kind of absolutely precise about this. You can see that in the given field of view, so this mesh is actually about atomic distance, so this would be probably about, I would say, maybe 50 angstroms, maybe so like 100 angstroms. What you see is actually, you see quite a few defects coming in. And so these materials are quite a bit disordered. Maybe not in the sense of the total conductance, but locally there are some defects. You can see them. So just to repeat the machinery, then we will put the local impurity, which will be magnetic or non-magnetic. I will use this Dirac Hamiltonian, assuming that I have some protection if I have a gapped bulk. And then I will proceed with calculating T matrix for multiple scattering and then plugging it back into the full Green's function. So this piece here measures the modifications of the local density of states. And from this Green's function, I can take the imaginary part on the particular site and measure what the total density of states look like as a function of energy. Or I can look at the spin projected density of states, or spin up and spin down.
Excuse me, ask a question here. So this Hamiltonian is a long wavelength approximation or something, some lattice model presumably from which it comes. So let's say in the case of graphene, you actually have to solve a lattice model at a small length scale. So and here you put a local impurity. So how can you use long wavelength approximation to describe the local impurity?
It doesn't matter. You can use it basically in the type value. The answer will be the same. So I'm going to show you something which we solved in continuum, but I will show you also the even density functional calculations. So here is the result for the thing is essentially copies, not that we copied it, but basically it copies the answers we know for D-wave for graphene. If you put defect, it produces resonance. And somebody was asking me if you put the so there is still kind of, even in the presence of spin-orbit coupling, there is this double degeneracy coming from this combined chirality in the topological insular. But if you put magnetic impurity, for instance, it lifts up this degeneracy, and there will be two resonances. One of them moves to the left, and one of them moves to the right of the chemical potential. It's kind of similar to what you would guess for the graphene case. If you have magnetic impurity, you will see basically doubly split. What used to be a spin degenerate state will split into two. Oh yeah, the functional dependence of this is the same. It goes like with impurity potential. So this actually is the density of states, the function of energy, and then inward in the plane, those are ripples drawn in Mathematica. This is a continuum calculation where you see how this ripple stay with the relevant wave vector, which is the K Fermi. Because now in this case, in the case of topological insulator, we assume that the Dirac cone is at the gamma point at center. Now, for magnetic impurity, it really depends which way you point the spin. So for instance, if I put the spin out of plane, it will be swirl. And this is because of the strong spin-orbit coupling. If the spin is pointing inward, it will be opposite swirl. And then if the spin is actually laying in the plane, there will be some dipolar configuration. So interesting question. Well, there is a slight tilt actually out of plane, which is shown here by the gray versus white background. Interesting question would be, for instance, what happened with the RKKY-like questions, interactions, if I have more than one spin or magnetic impurity on the surface of topological insulator. So if you sum up all this kind of like single particle space to calculate total spin density at the distance r, in this case we take it to be at the zero chemical potential, which is not realistic for the topological insulator as grown. Just was for the problem of pure Dirac cone with this spin-orbit coupling. Then we'll see that there is the Dzieloshensky-Baria piece that exactly how the particle flow symmetric case vanishes. Then there is the induced piece, which looks like it will be responsible for ferromagnetic coupling. And there is the dipolar piece. And they all die off at a certain distance, with a distance like 1 over r cubed. And by the way, this is very similar to what people expect for graphene. Now, if I look at the two spins and I look at the crosstalk between them and interaction term, so in other words, I'm reducing the spin due to the on the side 1. I'm looking at the spin polarization induced by the spin localized at side 2. So when you do the integral interaction, you'll have two pieces that are surviving for this Hall-Field case. One of them is a ferromagnetic one, and one of them is a dipolar one. So this one is responsible and knows about the spin-orbit coupling because directly coupled spin to the distance. So if you look at what this term prefers to do, it prefers to point these two spins toward each other along the line, and the ferromagnetic ones basically doesn't care. So you play with the numbers and you find out that if the spins are pointing out of the plane, they take advantage of -1, and they have a 0 for this energy because S dot into the unit vector along 1, 2 direction is 0, so this term is 0. So there is the energy gain of -1, and if you want to maximize the dipole piece, then you will get the energy gain of 3/2, but you have to lose 1 because you have to pay the price for ferromagnetic coupling. So the answer is actually the global minimum for this spin is actually all the spins prefer to point out of the plane. So they do prefer to couple ferromagnetically, and it's like as if spin-orbit coupling produces an easy axis and likes to polarize all the spins out of the plane. And in this case, there is no beating, so it's not the RPQI that takes advantage of peaks and troughs in the oscillating function. It's just basically playing with the power law tails. Now, since it's such an important question, let me just...
What is the scale of length corresponding to, let's say, a given temperature above which this effect will be killed by the temperature? Because I suspect the exchange is decreasing.
Yeah, so the brief factor there is a J dot S, so it's like a few millivolts maybe. So I think actually...
It's still pretty high.
Yeah, no, it's not millikelvin energy scale. Those are the quantum chemistry scales. Now, so since it's an important question, actually, people are asking about what exactly happens, and since I'm doing this like analytically, always some kind of like approximated calculation, and since the phase for the topological insulator as a phase is predicted based on the band structure, I don't have to worry about the Hubbard terms. I don't have to worry about the strong correlations. We can use the ab initio methods to look at the response of the topological insulator to magnetic and non-magnetic impurities. And unfortunately, I don't have a complete answer. Okay, so I'm not sketching, we just don't have it. But what we have is actually, we can look at the magnetic and non-magnetic impurities deliberately placed, replacing bismuth. So here is a bismuth selenium-3, and it's a stack of about 12 layers of bismuth, where we do the following. We go on top layer and replace some of the sides of bismuth with either iron or tin. So one of them is magnetic, one of them is non-magnetic. And then for iron, respectively, I can put the spin in the plane and out of plane. Now, but the problem is that I don't have a full density of stasis because, as you will see, the mesh in the K-space is not very good yet. So for the raw bismuth 2 selenium-3, you do recover the Dirac point. There is a little bit of a mini gap because of a crosstalk of the top layer to the bottom layer. And all these multiple bands are coming from the finite size quantization, or finite the fact that actually the slab along T direction has a finite number of layers. Okay, but we do have this kind of Dirac point, so had it been solved completely, all of these layers would collapse to one multi-degenerate band, which forms the Dirac point. Now, if I look at the tin impurity, then I can measure the band structure on the top layer and plot a projected band structure for the sides where I have a tin, and look at the bottom where I have a clean surface, and we will see that there is very little change. Now, in a way, actually, then it means I don't know exactly whether there will be this impurity resonance for the tin. So I don't know what comes out from this one. But for iron impurity, there is already something very interesting, at least at the calculation we've done. So I can look at the iron impurities, the 4 of them on the top layer, which I can line them up out of the plane, or I can put them all in the plane. So let me show you first a calculation where iron spins are all parallel to the surface, and therefore they should not have any effect as far as the gap opening. And indeed they don't. What you see is that you can do the fully self-consistent solution in the presence of spin-orbit coupling. This gap here is actually the gap because of the numerical calculation. Actually, it's a finite system, and so this is actually not significant. This is not the gap due to this like additional iron. This gap would be present there even for the pure graphene. For the pure bismuth selenium, bismuth selenium. But then actually what we can do is actually we can turn on spin-orbit coupling at the last stage, or we can do it fully self-consistently, and there is very little change. So as long as you ignore these kind of modifications, there is no gap opening, there is no additional feature. What's more surprising is actually, at least in this calculation, putting spins out of the plane doesn't change the result either. So whatever would be the density of states, whatever would be the band structure, we don't see any additional gap opening for the spins out of the plane. And so we will continue, and at some point we'll get to the bottom of what's really happening. But I would say that actually, the way it appears to me that when you look at the discussion of what effects of magnetic impurities is, that people often use this very simplified Hamiltonian where I look at the Dirac Hamiltonian, and I have essentially the homogeneous, like non-scattering, like external field produced by the spin polarization. what this calculation forgets to do is actually to say that, or to note that any of these impurities come also with the local scattering potentials, which are non-magnetic. You cannot bring in magnetic impurity into crystal without having some scattering induced as well. And so what happened actually, I think it's certainly true that this term itself will open up the gap, but in addition, my working hypothesis would be that, or my expectation would be that there will be some intragap resonances. And so the net effect, of course, is that actually some of these is if we also have all the spins lining up out of the plane or implied magnetic field, we do have a gap opening, but there will be some, call it intragap states inside that are induced by scattering.
Can I ask a silly question?
Sure.
When I look at those two terms, there are two things. Okay. The eigenvalue there I was expecting to be z plus az squared, not the way around.
Oh, this is actually kx and ky only.
Say it again?
This is our uniplane only.
Okay. The other question is, you see, k it's a vector, and z it's a pseudo vector, so the parity of the Hamiltonian is strange.
Yeah, it's because basically I have already it's like external magnetic field.
Okay.
This is like all the spins are locking up in the ferromagnetic configuration.
Okay.
I know you so you catch up.
So, do you hope at some point to try to get that triangular type shape that those guys see?
Sure, I mean it will come out as no-brainer basically. If you resolve it in a tight binding, it comes out.
Sasha, if you have excitonic excitations, then the gap opens, you don't need any spins at all.
Yep.
And then this central level is excitonic level actually.
Could be. No, I certainly would agree with you about excitonic or some levels. Basically, there is plenty of room.
Especially in 2D. You
Intragap
can
state.
screen Coulomb in 2D.
Here's Victor what happens. I agree with you that there could be some additional interactions. The protection, at least, is coming from the fact that if you have a shrinking phase space, you don't have this log, Kondo log, or you don't have a BCS log. And so you need to have a coupling that's bigger than critical one to open up the gap. So I'm saying actually, it's, like I said, there is always hammer big enough to destroy it. There is no such thing as unconditional protection. So if you want to destroy, open up the gap by applying, so like by turning on the interaction, certainly there is an interaction big enough to do it. So let me show you then, as a message. So here is actually what happened in graphene, pristine case with impurity-induced resonance. Here has happened for D-wave. Obviously there is a big difference. This is four-fold coordinated, this is square lattice, this is honeycomb. So let me show you something for topological insulator. This is topological insulator, and this is unpublished data. So you do have this, maybe kind of this peak will get sharper. It is possible that this peak is due to iron or magnetic impurity. But all I'm saying actually, in addition to what discussion was so far, there are some intragap or inside the Dirac cone resonances induced by impurity scattering.
Why is the blue line so asymmetric in the topological insulator?
Just have a look at take a look at the true timing data there. It's because basically there is no particle full symmetry. Even in the band structure, you can see that the field states, let me show you. The field states have less of a dispersion. Effectively, it means that they have a larger density of states.
Only if you come close enough, it does have particles.
But you're talking about experimentally, or you're talking about your calculation?
I'm not doing calculations. I'm just saying your calculation.
So my calculation is here. It doesn't predict the particle.
Gap.
Say it again.
Your calculation has a gap there.
No, this gap. Don't worry about this. This is actually way out of the accuracy for this method. It's not about the gap. So here, this calculation doesn't have a gap. But basically, if you sum over all k states for the band structure, this is actually the problem here is that we have to look at the small enough system because of impurity. But if you take a pristine bismuth selenium 3, the chemical potential will be somewhere, I forgot where, somewhere up here, and the Dirac point will be 0.3 electron volt below. But you can see that the pull down, actually the states below the Dirac point actually are flatter, so they will correspond to larger density of states.
So is the Dirac point particle hole symmetric close to the point or not? Sounds like it's not from the picture.
No, it's not. So that's what I'm saying actually. Even for the band structure, it doesn't have to come as exactly as a graphene case.
So that's because of presence of a quadratic term in K dot P partition theory, or
That's because of the band structure. It just
there must be a K dot P explanation for this.
I'm sure there is.
No, about 16 or so.
I'm sorry?
Well, if this is like literally two crossing lines close to the point, and they have the same
They
slope
don't have the kind
around
of the
the
same
line.
angle. Sorry.
But then there's a cusp in this line.
Yeah, exactly. No, but the cusp of the line is exactly what's left over of Dirac point. So this actually, you're taking me off on the kind of tangent here. But basically, if you open up this whole thing, I can show it to you in the papers. But there is more than one paper. But you know, this is actually conventional
But
material.
Is the density of states, or is the IDV is the density of states, right?
It's a local tonic conductance, yes. And so the Dirac point is always commonly believed to be, unless it's doped, is about minus 300 millivolts, which is consistent with this ARPES data. But the dispersion of the ARPES actually, I don't think is symmetric either, and above and below the Dirac point.
Even in the immediate
Yes.
proximity of zero energy.
Yes. So,
But maybe,
Was it because of gravity?
maybe if you look at the very, very
okay,
bottom,
so fine.
it's just a parabolic thing.
Fine. This is not the main point here, basically. I'm not ready to really, what I say, to pick up the fight about this. It's fine, whatever it is. If it makes it, so the point actually, when I look at the total density of states, I have to sum up over other bands. If you look at the ARPES, well, we can show it at the end. Basically, you can see that there are contributions from the other states, and maybe it's actually right in the middle vicinity it's symmetric, but the rest are like quite a bit of more states on the field side than on the empty side, even in ARPES. So let me just conclude by saying that the Dirac material is a class, and there are some similar response, which basically you can look at this. If you have sort of Dirac point, then you can make few predictions about what will happen. And what I spent a great deal of time is showing you how impurities in local probes are useful to investigate the states. In case of the topological insulator, we will plan to continue, and I would encourage you to look at this in a straightforward fashion to see what happens with the suppressed backscattering and how exactly impurity scattering modifies the tonic conductor. So what we find is that impurity-induced resonances in topological insulators are very similar to the other ones in other materials. And so with that, thank you.
Questions?
So, if you have magnetic impurities, given that the density of states goes to zero, would you see any condo-wise upturn in resistivity?
Well, it's the same story as with the excitonic one. You don't have a standard condo log.
I know, but also what would you see with the impurities?
So you would see the condo. It's possible that you can see condo effect with the coupling constant again if the exchange is big enough between the localized spin and the conduction band.
No, I'm not talking about condo effect per se. I'm talking about resistivity as a
Oh, there will be upturn. I don't know if it will be logarithmic or not. The log comes from the standard metal. No. No, I think actually for iron doped bismuth selenium, I don't think people see the upturn in resistivity.
I have a question. So, usually people say that you can show by a supersymmetric signal model that for non-magnetic impurities cannot localize states of the age, at least weak impurities.
Right.
But so would you agree with this statement, or you don't? I didn't quite understand what happens with non-magnetic impurities.
So you have to tell me what you mean by supersymmetric sigma model. Are you averaging over impurities?
Well, yeah, it's a method for the average.
I'm talking about single impurity and otherwise pristine material.
Well, people typically believe that as long as disorder is weak, so disorder, if impurity is very strong, maybe they cannot say anything. But as long as it's weak, and in this case, weak would probably mean.
Yeah, what's interesting actually? What's the
gap?
So what's the band gap in this material? 0.3 electron volts. That's a relevant thing where you have a spin orbit protection. How much of the energy you're messing up when you're bringing iron or calcium or some other material? Let me just say.
Then I agree with. I'm asking more theoretical questions. So when you do get those states, what kind of impurities do you use? Strong or
I'm using strong impurity. I'm using unitary impurity, but the point actually here, compared to graphene, in the graphene case, impurity should be unitary on the scale of the bandwidth of graphene, which is actually Dirac cones on the scale of like a couple of electron volts. Here, I have to have a strong impurity on the scale of the Dirac cones on the scale of 0.3 electron volts. So my point is pretty much any substitutional impurity or any defect actually has enough energy on the quantum chemistry level to overcome this. So here's an example. So since you've been asking about the where this protection can go wrong, all right. It mentions the following second-order process. I take a state from the Dirac cone, and by paying 1 electron volt price in the denominator, I take the state in the conduction band, scatter it up, scramble it, and come back. So usually we ignore this because basically if the matrix element for this process is you have to pay electron volt denominator energy, you tend to ignore this process. Here I have electron volt in numerator, and I have 0.3 electron volts in denominator. So there is more than one pathway to mess up this protection.
More questions? Let's together again.
So is the schedule tomorrow, is it published?
Yes. Yeah.